Okay, so finally we are going to prove, a famous and beautiful theorem, and the proof is very nice. You will enjoy it, which is the Euler's pentagonal number theorem. Okay, so and we are going to use generative functions to prove this. There are several proofs, but this one is in particular very beautiful. So we start with something that we have already seen, right? The generative function for integer partitions. We proved that it is product I equal to 1 to infinity 1 by 1 minus x raised to I. Now, let us define dp to be the set of integer partitions whose parts are all distinct. So dp is a distinct partition, right? So each part must be distinct. I don't want a partition of integer. So if I am looking at the partition of, let's say, partition of 10, right? I can write it as 2, or maybe let me. 442, but this is not allowed to be in DP, right? Because the parts are not distinct. So I don't want such partitions, right? So I want to avoid these kind of things where parts are repeated. On the other hand, this is a partition where the parts are distinct, so therefore this is allowed, right? So we want to look at the set of all integer partitions where the parts are distinct for any, right? So therefore look at all possible integers. For each of them, look at the set of partitions, and in which the parts are distinct, and collect them together. So that is the set dp, right? Now we want to look at the generative function for dp. Okay, so let us see what is this. So first we observe that for each number I, right? When we are deciding the partition, right? But as we did in the case of 10, for example, right? Each number 1, 2, 3, 4, 5, etc. We have a choice, right? Whether we want to add I into the partition mu exactly once or not to add it, right? So for every I, we have a choice, either add it once or not at all. Then that's okay, right? But if I add, I can only add it once. Now, as we just noticed, right? This choice is given by the generative function 1 plus x raised to I, because if I choose either x raised to I say that I have chosen I to be in the partition. And if I choose 1, then I say that I is not in the partition, right? So, then if you look at the product 1 plus x raised to I, right, where I ranging from 1 to infinity, that tells that, I am choosing, either exactly one copy of I, right? For any integer, I am going to choose only either exactly once or nothing, right? And therefore, this is the generative function for dp of x, right? That is something very clear to us. Now that we can get by product formula. But on the other hand, what is dp of x by the definition of dp, right? dp says that dp is the set of all partitions where each part is distinct. Now, because of this, how do I get the generative function, right? So because each part is distinct, and I sum over all the elements in dp, right? X raised to what number it is representing, right? So if the partition is representing, let's say, n, right? The partition of n, then x raised to n is what we want to say, right? So because we want to find the coefficient of x raised to n to count exactly the partitions of n, right, which belongs to dp. And another way to say is that it is summation over all mu in dp. x raised to cardinality of mu. So therefore, whenever the size of mu, right? So whenever the size of mu is n, we will look at the partitions mu which belongs to dp, and how many are there? That is precisely the number of such partitions, right? So therefore, this is the definition of dp of x, right, in another way. So we know that summation mu in dp x raised to size of mu is the product I equal to 1 to infinity 1 plus x raised to y. So we got the generative function for dp, right? Now, so we started with the generative function for the integer partition, which is 1 by 1 minus x raised to y, right? So let us now, so there is some kind of similarity between these two things. Especially if I, instead of looking at 1 by 1 minus x raised to y, suppose I look at the product of the reciprocals 1 by 1 minus x raised to y, right? So if I look at 1 minus x raised to y, the product, right, it is just the reciprocals in the generative function of the partitions of integer I, right? Partitions of an integers. Then it is very closely related to product I equal to 1 to infinity 1 plus x raised to y, because I am just replacing x with minus x, right? So because of this similarity, I am doing this, and the fact that the Euler's pentagonal theorem is about the expansion of this product. Okay, so and what will be the terms in the expansion? That is what the theorem is about. So let us now look at this product, which is very much related to the both, right, in two different ways. This product is related to the distinct parts generative function by changing x to minus x, and also related to the partition for integers as reciprocals of the factors, right? So therefore, this is related to both, and we are going to use this relation. Now, suppose we are given a partition of some number, say mu is equal to mu1, mu2, etc., mu s. So there are exactly s parts. So the length of mu is s, right? So if you recall, when we studied partitions, right, integer partition, we said that length of the partition denoted L of mu is the number of terms, right? Number of parts. So given a partition mu, mu1 to mu s, the length of mu is precisely s. Now let us again look at summation, product I equal to 1 to infinity 1 plus x raised to y, right? Which by definition is summation mu in dp x raised to size of mu. Now, when I change the sign of x to minus x, right? So then what happens? So I get not x to minus x. I'm changing the it's not changing x to minus x. Sorry, it's changing the sign from 1 plus x raised to y to 1 minus x raised to y, right? So I have product I equal to 1 to infinity 1 minus x raised to y. So how can I represent this in terms of the summation that we have? Okay. So I claim that this is actually equal to summation mu in dp minus 1 raised to length of mu x raised to size of mu. Now, can you think why this is precisely the case, right? So if you look at x raised to size of mu, right? We are looking at the coefficient of, so let's say mu is the partition of n. Then if you are looking at x raised to n, how do I get the term x raised to n, right? So x raised to n comes from the partition mu, right? And the partition mu is, let's say, mu1 to mu s. Now, how did this x raised to size of mu, right, x raised to n came about? Well, it came about because in the product on the left side, right, we have 1 minus x raised to y, And what is 1 minus x raised to I saying? That I am choosing minus x raised to I if whenever I am choosing I, right? So when I choose mu1, right, I am basically choosing minus of x raised to size of mu1, right? Right. Similarly, for every I, I am choosing minus x raised to size of mu I. So minus, there is no bracket here, so therefore it is negative, right? Or minus of x raised to size of mu I. And then when the mu I is add up to n, right? The size of mu I is add up to n, then we get mu itself, right? So therefore, when I obtain x raised to right size of mu, I have taken how many copies of minus x raised to I, where I is ranging from some numbers. Precisely length of mu many copies of minus x raised to I have taken, right? Minus x raised to I, minus x raised to j, minus x raised to k, etc. Right? And if there are odd number of negative terms, then it is the product is odd, and otherwise it is even. So therefore, if I look at minus 1 whole raised to length of mu, it accounts for the sign, right? By length of mu is odd, then I get negative, and length of mu is even, I will get positive. So that explains why this summation I equal to 1 to infinity 1 minus x raised to I is the summation over all the distinct parts, right? Mu belongs to dp, distinct partitions, minus 1 raised to length of mu x raised to size of mu. Now we are going to use some trick, right? So we have learned about involutions earlier. So given a partition mu, let's say mu1, mu2, etc., mu(s), of course, we will assume that mu1 is greater than mu2, etc., greater than mu(s), because in a partition we order them according to the size, and since the parts are distinct, we know that it is never an equality, right? So mu1 is strictly greater than mu2, greater than etc., greater than mu(s). So mu is in the distinct parts. Let us say that the largest index of index, let's say a, for which mu1 to mu a are consecutive numbers, right? So let us say that mu1 and mu2 are such that mu2 is exactly mu1 minus 1, mu3 is exactly mu2 minus 1, etc., up to, let's say, a, right? So if you so we are looking at this specific type of partitions. Not specific type of partition. We are looking at the partition then deciding up to which number we can have this consecutive numbers, right? So let us see. Yeah, so here is an example at partition, the Farage diagram. If you look at this, you will see that here I have 1, 2, 3, 4, 5, 6, 7, 8, right? The first line, there is 8. So it's the partition with the first time is 8, right? Mu1 is 8. Then we have 7, which is mu2. Then we have 6, which is mu3. But then mu4 is 4, which is, right, it's not consecutive. So 8, 7, 6 is consecutive, but the next one is not. So therefore, my A is now 3, right? So this is how I choose A, right? So A is the largest index for which mu1, mu2, etc., mu A are consecutive numbers. Then we define B to be, B is equal to mu S, which is the smallest part of mu, right? The last part is B. So in this case, what is last part? Last part is 1, 2, 3, 4, right? So last part is B. So given any partition in DP, we know that mu1 greater than mu2, etc., mu_s, and we can always, so we have a non-zero index because mu1 is always there, so a is at least 1, so it will be between 1 and s, right? And therefore it is well defined, and we have a and we have b is the last part, so therefore a and b are well defined. Now we are going to define an involution, right, which takes partitions to partitions, right? So I'm going to transform the partitions by defining an involution. So if a is less than b, right, so we have defined a and b. If a is strictly less than b, then I define the involution I of mu1, mu2, etc., mu_s, right, as going to, so I of mu1, mu2, etc., mu_s is the partition by subtracting 1 from each of the first a terms, right? Because there is a consecutive numbers are there, mu1, mu2, mu3, etc. And therefore, I can subtract 1 from each of them, right? So from mu1 I subtract 1, mu2 I subtract 1, mu3 I subtract 1, and then a I subtract 1, right? So I have subtracted a1, so therefore totally I have subtracted a. Now since a is strictly less than b, I can add a as one part at the end, and then the total will still be the same, right? So I am going to do that. I take mu1 to mu_s. From the first a parts I subtract 1, right? Then all the remaining parts I keep as it is, mu_a plus 1 to mu_s, and then I include a new part, right? The number of parts is now increasing, right? And I am adding mu_s plus 1 is equal to a, right? So because a is strictly less than b, we know that this is definitely a partition of mu, right? Again, so therefore the involution does not affect the total, right? It keeps the size of the partition or area of the shape of the figure, right? The area is fixed because I'm just rearranging the cells, and because mu a plus 1, right? So this is basically strict. We know that when I subtract, these numbers will never be larger than mu_a plus 1 to mu_a. So therefore, this will be still non-increasing sequence. So therefore, I have defined a partition by doing this. So I of a is and I of mu is another partition. So I of mu is obtained by decreasing the first a parts by mu, and by adding the part with size a to the last part of mu, right? So here is the pictorial representation of the same. I start with this partition, right, where I have these numbers, and a and b are here. A is less than b because a is 3 and b is 4. So therefore, I put this a, right, the 3 elements. I'm moving them from there. I have reduced the numbers from here, and then putting at the last part, right, which is b, right, below the b that we have. And now for this, again, now we can look at what is a and b, right? So if you look at the a and b, you will see that b is now 3, a is 1, 2, 3, 4, and 5, right? So therefore now a is larger than b, right? So we will define the involution for that also, and one can be defined in such a way that its involution will be the original image itself. And similarly, here is another example. We have a and b, where this a is reaching here. I again put it here. I get another map. So I have I have the involution of the first figure. Right? So what is the other case, that if A is greater than or equal to B, if A is greater than or equal to B, then I takes mu to mu 1 plus 1, mu 2 plus 1, etc. Mu B plus 1, right? Mu subscript B plus 1 to mu A and mu S minus 1. Okay. So what I do is basically removing the last part, right? The mu S is the last part. I remove mu S from that and distribute. Mu S is actually equal to B, right? The smallest part is B. And distribute this B to the first B times of mu, right? So I'm going to add 1 to each of the first B parts. Since A is greater than or equal to B, I have the leverage to do this. So I add add these parts and I get the involution, right? So I of mu is obtained by removing the last part of mu and increasing the first B parts by 1. Now the claim is that I is an involution because if I look at I of mu, it is equal to mu. And this is something we can verify, right? Now it preserves the area because we don't remove any of the cells. We are just moving around the cell. So the total is going to be the same. But on the other hand, it is sign reversing in dp. Why is it sign reversing? Because if you are going to get distinct parts in the new mu, right? If the new partition at I of mu is having distinct parts, then the number of parts has changed by 1, right? So the length of mu is changing now, right? So length of mu and length of I of mu differs exactly by 1. So in the summation, the coefficient, right, minus 1 L dash mu, right, that sign has changed, right, for this particular partition. So it basically is a map from partitions to partitions where, for the first partition and second partition, if both of them are, in dp, then the sign of them are opposite. They are distinct partitions, they are different partitions, and the signs are different. So if I can match up this, those terms will cancel out in the summation, right? So if I'm looking at the summation here, the corresponding terms will cancel out, which means that in this product, right, the product is basically the expansion of this product is precisely the way we are obtained here. So we need to figure out which terms are going to cancel out, right, in this product, and that is what our aim is. So we have defined this involution and see whether there is any problem with this involution or if any of the terms are remaining, right? So there will be some cancellation because whenever mu is going to I of mu and mu and I of mu are distinct partitions, we know that those two will cancel out, right? Because they have different signs. The involution is a sign reversing involution. So we now observe that not all involutions of mu are going to be in dp. Okay, so only those in dp will be counted by the summation. Therefore, only those pairs will cancel out. So we need to figure out which are the ones which are not counted in dp. So there are two cases. Okay, one is that like if b is equal to a plus 1, right? So if exactly a plus 1, in that case what happens? So b is here 5 and a is 4, right? And if b is actually equal to a plus 1, when I remove these 4 parts, right, the last 4 cells, right, and we are going to put it below b, what happens? I am going to put 4 cells below B, but now B has decreased by 1, right? So, and therefore we have 4 new parts coming here, where these parts have disappeared, right? So we are getting a partition, but the last two parts are the same, right? Because there is 4 here, B become B minus 1, and A is also equal to B minus 1, right? So therefore, these two parts are having exactly the same size. So two same numbers are appearing, and therefore it is not in dp. I mean, it's not dd, it is dp. Right? So I of mu is not in dp for this case. So we have I of mu, but then I of mu is not in dp. Therefore, this term will not be cancelled. So we can say this is a fixed point. Okay. Now, there is another case when also we have this issue that is when B is equal to A. So if B is equal to A, then we cannot define I of mu, because when I take away the A parts, right, then A becomes larger than B minus 1, right? B we had how many times the last part is also removed. So therefore, if B is equal to A, then what happens is that when you remove the last part, it becomes B minus 1. I cannot put A below it. So therefore, I cannot really define I of mu. So I of mu is undefined. So therefore, I can say I of mu is mu itself. So this is again a fixed point. So whenever I of mu does not belong to dp, we will say I of mu is equal to mu itself. So now our involution is now defined well, that whenever we can define I of mu to be in dp, I define I of mu in the previous as in the previous example, and these two cases I will define I of mu to be mu itself. So therefore, I have the involution, and we know that I of mu is precisely mu itself. And once we have this, so here is the written explanation that if A is equal to length of mu and B is a plus 1, then as we observed, I of mu is not in dp. And in that case, we have to set I of mu to be mu itself. And similarly, if I cannot define this because the length of the part that I am going to add is more than the last part in mu minus 111, right? We have to define I of mu to be mu itself. So therefore, these two terms are fixed points, and all other terms are not fixed, and therefore they will cancel out. So when exactly this happens, right? So when exactly are the fixed points there, and fixed points are the only ones going to survive in the product. So therefore, and in the sum, right? So let us analyze this. So we can see that whenever mu is of the following form, this will happen because we want the numbers to be consecutive, right? So if mu is 2k, 2k minus 1, etc., 2k plus 1, right? And it has exactly length k, right? So the length is k, there are exactly k times here. And then, of course, what is the area of this? I have to just add these two elements, which is k into 3k plus 1 by 2, right? Or if mu is the case, 2k minus 1, 2k minus 2, etc. up to k, right? Where again length k, right? Instead of starting from 2k, I start with 2k minus 1. And again, the size of k is k into 3k minus 1 by 2. In these two cases, we can verify that case A and these two previous cases, right? This case and these cases will appear precisely in this case. So this is something one can manually verify, right? Because we are partitioning a number with this property, right? The sizes are now well defined, because here everything must be decreasing. Here also everything must be decreasing one by one, exactly consecutive. And these two cases will happen precisely when the numbers are either of this form. And area is precisely the sum of the numbers, so therefore that is also clear. So these are the fixed points one can verify, and then the empty partition, of course, is also a fixed point, right? It's not cancelled, and therefore we can use this information to define the product from the summation formula, right? So what are the terms that is going to survive are precisely when the power of x is either the size is n into 3n minus 1 by 2 or n into 3n plus 1 by 2. And in this case, the sign will be minus 1 raised to n, which is the number of times. So n is the number of times, and the area is n into 3n minus 1 by 2 or n into 3n plus 1 by 2. Right? So summation n equal to 1 to infinity is and plus the 1 for the empty partition. And that are the terms which are going to survive. And what is this? If you expand this, you will get 1 minus x square plus x raised to 5 plus x raised to 7 minus x raised to 12, etc. So these numbers which are appearing in the exponents are called the pentagonal numbers. And this result is known as the Euler's pentagonal number theorem. Pentagonal number theorem. And this is a very nice and well-known result. Something comes a lot in mathematics, and very beautiful result. And we have a very elegant proof of that. And I think with this application, we can conclude our visit to generative functions. And there are more techniques that one can learn, but we will keep that for an advanced course. And here I will leave you with some few exercise questions which you can try out. So the questions include, the first one is, let Hn be the number of compositions of n into parts where each part is either 1 or 2. Okay. If H0 is 1 and h of x is summation Hn x ratio n is the generative function, find out Hn, right? Find a formula for Hn. Second question calls to look at the derangements. Right? We know that we have solved the derangements using the inclusion exclusion, right? The formula for derangements, and we have shown that the formula is dn is equal to summation I equal to 0 to n minus 1 raised to I n factorial by I factorial. Okay, so this is something that we have proved. Now find the exponential generative function for the derangements, right? Let's say der of x, and try to find it in a closed form. Then find the exponential generative function for the Bell numbers that we have discussed in when we are looking at the partitions. And finally, here is another very interesting question. Suppose you are all familiar with the dice, right? The 6-phase dice with the numbers, the dots 1, 2 up to, let's say 6, right? So there are the 6 phases. Each phase has distinct number of dots 1 to 6. Now let us say that these phases are this dice is picked up and rolled, right? So there are 2 of them, so I roll them. Now the outcome of a roll is basically the sum of the numbers on the top. Okay, so take the numbers on the top or number of dots on the top, count them. Now because it is 1 to 6, the count, right? Some of these 2 will be ranging from 2 to 12, right? It can 1 is happening, it's 2, 3 and 4 or 5 and 2 are happening, or 6 and 1 are happening, you will get 7, etc. Right? Up to 12 is possible, and these are the only outcomes that we can have from this rolling, right? Now then, what we want to do is to use generating functions, right? So find the generative function for counting the number of ways the sum 2 to 12 can occur, right? So whenever 12 is happening, the coefficient of x raised to 12 must be the number of ways that can appear. Now use this generative function and try to play with it, right? And show that there is another unique pair of dice that we can come up with. So the 2 dice, but the numbers are going to be different, not 1 to 6. It will have some other numbers. So can you define, can you show that there is another set of 2 dice, 6 face dice, where the numbers of the sides are slightly different from 1 to 6, but with the same outcomes, with the same probability, that the number of ways each outcome, the number 12 or 5 or 3 or 2 comes is the same, right? So this type of dice have a special name. We will not, that is something we can find out later. Okay? So try to solve this. This is a nice question. It might take a little bit of work, but it will be worth the exercise. So with that, we conclude this introduction to generative functions, and we will see more about it in advanced courses. Okay, so with that, I wind up, and we will continue with a different topic in the next lecture.